In this video, we're simply going to discuss Stiochiometry, and we'll start by discussing measurements and units. And this is important because all the calculations we'll be doing, we are going to be demarcating the quantities that we'll be observing into two types. So whenever an experiment is being conducted, it's either you're going to be having quantitative data. So quantitative data, where this is also known as the numerical aspect of the experiment. You need to know the quantities you're dealing with, and also we need the qualitative part. So the qualitative part is where we have a description of what is happening, or the steps that are necessary for us to obtain the desired products. So we need to know what to do with our reactants to obtain what we're in need of. And these quantities are always going to be measured. So if they're being measured, we should be able to associate particular units with the quantities we're dealing with. For instance, in most cases, we'll be dealing with things that we have to measure the mass. So that's the reason why we will be measuring mass in kilograms or grams, depending on what we are discussing. So what I mean is, if you are told to do calculations, for instance, of density, you know, density is mass over volume, right? The units of density is just grams per watt, grams per liter, or you can say grams per cubic centimeters, or however you decide to put it. All we're just saying is that on solving, we always have to indicate the units of mass. You can't just say 2 over, let's say, 10, then all of a sudden you give us the answer to say it's 0.2 grams per watt per liters. You need to show the units here to be 2 grams in this liter, so that we get the appropriate units for the quantity that we are looking for. So that's the first part when we discuss measurements and units. So we have to always indicate the quantities that we are measuring. Now, when it comes to the numbers, which is, I just want to discuss a bit on significant figures and decimal places, just to remind you of what you learned in class. So significant figures, when we discuss about this, we have certain rules that we follow. All numbers from number 1 to 9 are all significant. All the digits 1 to 9 are significant. That's the first rule. Then we say trapped zeros are also significant. Yeah, so trapped zeros also become significant. And if you have trailing zeros after the decimal point, so trailing zeros are also significant. Then leading zeros are not significant. This is 3, this is 4. If you have leading zeros in front, so leading zeros are non-significant. So these are non-significant. So by 1 to 9, I just mean if I give you something like this. This here, all the 4 numbers are significant. If I give you 2, 0, 3, here the 0 is significant. This is 203. So the 0 is significant. We cannot ignore it. And trailing zeros, if I give you something like 0.00400, in this case, these zeros here are trailing after the decimal point. So they are trailing after this non-zero digit. So these become significant. So here you have 3 significant figures. Here you just have 3 as well. Then here you have 4 significant figures. The leading zeros are like these zeros in front. These are not significant. Yeah, that's what we mean by trailing zeros not to be significant. Then if you have a number, let's say 5,000, but there's no point here, just let it be like this. These zeros are not trailing, because trailing, they should have been a point. So this type of expression, only one figure is significant, which is the 5. But if I put a point here, these now become what? Significant. There will now be 4 significant figures. So please take note of that. Then when it comes to decimal places, we just say the digits after the point. So like here, there were no decimal places. Here, the decimal places are 1, 2, 3, 4, 5. How many digits are after the point? That's what we mean by decimal places. And these significant and decimal places are necessary because when it comes to calculations, when you're dealing with multiplication and division, you follow the one that has least significant figures. That's the one you follow. When it comes to addition and subtraction, you follow the digit that has least decimal places. So that's basically what you follow. So if you're multiplying 2.2, by let's say 6.34, your answer is going to be to two significant figures, because the number that has the least significant figure is the first one, which is simply the 2.2. So our answer here is going to give us, initially you're supposed to get a 13.948, but this is just going to be a 14 because we need two significant figures. So we put the 9 can round off here, so we just have a 14. Yeah, but if we're adding or subtracting, we get the one that has least decimal places. So please take note of this. In other words, whenever you're doing your calculations, if you forget all these rules that we are discussing, we're just saying, whenever you're doing calculations, always put your answer to two significant figures, right? Or some say to two decimal places if they're decimal places. So just follow this. This is a general rule. This is what they use to make all the answer schemes or the marking keys for all the assessments. Yeah, so this is a standard and accepted. So now the idea or the reason why you are learning about measurements and units is because of the conversions that are necessary. So this is a part what we call dimension analysis. The whole reason why units are very vital is because your dimension analysis, so dimension analysis is us just working with the units to verify that the quantity that we're, or rather the units that we're getting as the final units will align with what we are looking for. So a typical illustration is being told to convert something like, they're saying convert 10 kilometers to miles. So this is simply the whole process that we need. So now look at this. I'll pretend you have not seen the final answer at the end. So let me just move this guy here. Yeah, so let's pretend as if we haven't seen the working. So they want us to convert 10 kilometers to what? To miles, right? That's what they want. Then they've told us that 1 kilometer is equal to 1,000 meters, and 1 meter is equal to 1.094 yards, and 1 mile is simply the same as 1760 yards. So how can we arrange these given conversion relations to cancel the kilometers until we have miles at the end? So we're simply going to say this is going to multiply. We're trying to convert the kilometer to meters, so we'll put the meters on top. Then we say 1 kilometer down, so that I just want the kilometer to cancel. Then this will multiply. I want the meters to cancel, so I'll put 1.094 yards on top. Then I just say 1 meter, so that 1 meter cancels. Then again, I want to cancel the yards, so I'll just say 1 mile is the same as 1760 yards, so that I have the yards again cancelling. You notice that by the time you are done, the only units appearing are miles, and you have 10 multiplying 1,000 multiplying 1.094. Then down, you just have a 1760 miles. So this is what you get. If you multiply this, you get what they got here as well, which is your 6.22 miles. So we have to arrange these conversion relations in a way that will cancel kilometers. By the time we are done, we should remain with what? With miles at the end. So this is what we basically mean when we say dimension analysis. We're just using units. So using units. So this is when we use units. So using units to do calculations to obtain. So this is just the whole idea is to obtain the desired unit. So the unit that we were desiring was miles. So that's the whole conversion. In the end, you notice that you now know to say 10 kilometers converted to miles is simply 6.22 miles. So now we know to say this is the number, but the units are what was leading us. So this is basically what we mean by dimension analysis. To conclude this, we're just saying always indicate the appropriate units whenever you are making your calculations. Yeah, that's what we are basically emphasizing here. Yeah, it's always mandatory that you do so. Now, the second part of more concept is simply a part where we look at, we discuss these this first part where we look at the periodic table, just the first part of the periodic table, by discussing what an atom is, molecules, and what ions are. So you know, to say an atom is anything that can make up element, the smallest thing that makes up what? That makes up elements, right? And it has what we call the mass number and the proton number. So you know all the basics, so you know this. And we know to say this has subatomic particles, which are simply protons and neutrons and electrons. And there are cases, or there are times when you can have isotopes. So isotope are simply atoms of the same element with the same. So there's, let's say, chlorine 34, there's chlorine 35. They're both going to have 17. So these are typical isotopes. Yeah, so this is the isotopes of chlorine. So we're just saying you can have something like this, atoms of the same element with different mass numbers, but the proton number is the same. So you can have this at times. And this is just a minor introduction to say the whole idea why they came up with the periodic table is because the elements on the periodic table are arranged in such a way that we can identify them using the what? Using the proton number or the atomic number. So this is what we have. And these numbers that you see here, these are given in decimals because these are like average mass numbers that you are seeing. Yeah. So they combined several isotopes to obtain this middle one. This is like the median that you are getting. So maybe you should make sense out of this. The mass values of copper 63, the percentages are given, and the average mass is that respectively. Calculate the average atomic mass of copper. So we're saying copper, the average atomic mass of something is equal to the isotopic mass of the first isotope and its percentage, the isotopic mass of the second isotope and its percentage, everything over what? 100. Or some people do it separately, so it's okay even if we say separately. The common denominator is still 100. You can say over 100 this side and also 100 this side. Then to give you the average, and the average is always given in, they say units or they say atomic mass units. Yeah, or sometimes they can say grams per mole. It's one and the same thing. Yeah, then you know to say if you are given a formula like, let's say, carbon dioxide, and they ask you to get the molecular mass, the molar mass of this, you know to say this is just 2 by what? 16. I'll use the one that is having whole numbers. Then you know this will just be 1 times 12. This will be what? A 32. This will be 16. 12. You know you get a 44. So this will be the molar mass, right? So hope you're okay with this. So molar mass is just the sum of all the molar masses of all the atoms represented in a chemical formula. So you are believed to know already how we come up with things like this. You know already how we come up with things like how water comes about. So we will not dwell into how we come up with its molecules, because we're expecting you to know to say, you know how you were taught in high school about valence numbers, and you know to say if you're having hydrogen, the valence of hydrogen is 1, the valence of oxygen is 2. So to make water, these guys just are going to be like this. So we swap the numbers. So these two come here on hydrogen, the one will come there. So now if they're asking for the Mr. or the molar mass of water, we just say 1, because there's a 1 here, right? So we say 1, there's 1 oxygen multiplied by the mass number from the periodic table. Then again, there are 2 hydrogens multiplied by the mass number from the periodic table. And this is the periodic table that we'll be using here. They'll always be giving you. Yeah, so no wonder for oxygen I'm using this guy, and for hydrogen I'm using this guy. So you use the data or the values given on the periodic table that you're using. So this is how we get the molar mass. Now, this whole idea, or the whole purpose of you doing this more concept, is to know how much you are going to produce. If an experiment is happening, we need to know how much we're expecting to get. You just need to have a theoretical anticipation on the amount you may be able to produce. Of course, there can be errors and everything else, but let me just give you what you need here. So This is specifically now where more concept calculations start. And what we need is what we call the relation between the Avogadro's constant and the number of moles. So this here is what you call the Avogadro's constant. We give a definition of a mole to be anything that contains 6.02 times 10 to the power 23 particles. So if I say I have 1 mole of pens, it simply means I'm having 6.02 times 10 to the power 23 pens. That's what I basically mean. So here it's particles because it can be anything. And if you say you have 2 moles of pens, meaning you just double this, right? Yeah, it's like saying you have 2 moles. If 1 mole is equal to this, 2 moles will give us what? You know, to say, I'll just cross multiply here, right? Then you get the number of particles. It will just double up. So this number here, the 6 point, this constant here, is what you call the Avogadro's constant. That's a Na, that's the Avogadro's constant. So in other words, if I was to give you to say an example, to say find the number of moles in, I'll just say 60, the number of moles of 60 eggs. So let's say I'm giving you eggs. You just do the same thing. 1 mole is equal to 6.02 times 10 to the power 23. The question has said eggs. So meaning here the name of the particles we're dealing with are eggs. So how many moles will give us 60 eggs? That's basically what we're doing, right? Now if you notice, you can cross multiply. This will be 6.02 times 10 to the power 23 eggs. These are eggs. Then multiplied x is equal to 60 eggs. Then more, that's what you have because of the 1 more times that. Then here we divide by 6. The Avogadro's constant, 23 eggs. It goes with its units, which is eggs. We have the 6.02, 10 to the power 23. These are eggs here. So this part can cancel. So meaning the number of moles that are found in 60 eggs, we cancel the eggs part. We just divide, so we're saying 60 divided by the Avogadro's number, the Avogadro's constant. So if you're doing the right thing, you should get something like a 9.97 times 10 to the power negative 23 moles. That's what you should be getting, something like this. So to avoid all these, we just say the first formula for you to get the number of moles, so the formulas that you need to know, the first formula that you need to use is just say number of moles is equal to the number of particles given over the Avogadro's constant. So this is where N is the number of moles that you're looking for. N is the number of particles given. And the name of the particles, then Na, this is 6.02 10 to the power 23. This is Avogadro's constant. Yeah, so this is the first formula you ever learn on moles. And the second one is also very simple and common. Number of moles is equal to the mass of something over the molar mass of that thing. So here I'll just say molar mass. So this sometimes can be written small letter m over mist. This is the second formula for getting the what? Getting the number of moles. So just to summarize all the formulas, I've already given you the first one and the second one. The other formula is this one here that says number of moles is equal to concentration times volume. Sometimes they say molarity times volume. So this is the third one. This other one here is simply for those that are taking Chem 1000. So you know that equation for saying under gases, PV is equal to nRT. So here we just make N the subject. So pressure, volume, number of moles, the universal gas constant, and the temperature. So number of moles is equal to PV over RT. That's where this guy is coming from. Then this one is sometimes used under electrolysis. We just say the number of moles is equal to current times time over the Faraday's constant. So this is basically what you have. But the most common ones that you have to know here under more concept are just the first two. The first three are enough. Yeah, of course, there could be other conditions for those that are doing Chem 1000. Sometimes they do they do use these following conditions to say every single mole at STP occupies 22.4 liters. So sometimes there's this volume to mole relation depending on the condition that you have. Then this is somewhere like a 24 liters. This is at RTP. And there are these two conditions. So STP means standard temperature and pressure. RTP means room temperature and pressure. So the first three are the common ones that we'll be using. Look at the first example here. They're telling us to say, they're asking us to get the number of moles in 5 times 10 to the power 20 cobalt atoms. So what's the number of moles? So we'll just use the first formula because we're given the number of particles. We divide it by the Avogadro's constant. Making sure that on punching, you put this in brackets. These have to be in brackets. That's when you get the correct answer. You have to tell your calculator to say this whole thing is a single number divided by this whole thing. Yeah, so if these are the moles of cobalt, you know to say number of moles is also mass over Mr. So you can now get the mass that was there. So you can get the mass that was present by multiplying the number of moles by the Mr. because you know it's cobalt. So you can get the Mr. from the periodic table. Yeah, so if you go to your periodic table, well, cobalt has a 58.9. So you can just get the 58.9 and multiply it. Yeah, so we can just multiply it with the number of moles and we'll get the mass. And the second one, they're saying how many moles are in this mass of hydrogen atoms. Hydrogen is a diatomic molecule. So meaning we have to multiply 2 by 1.008. We'll get our answer 2.016, something like this. So the number of moles will just be this mass, 0.2512. Then divide by the Mr, which is just a 2.016 grams per mole. Then you get your answer. Yeah, so you just look at the data that you are given. Then you what? Then you compute. Yeah, so here they should have used the one that I used because hydrogen is a diatomic molecule. So here they're saying hydrogen. If you just say H, this is such a symbol. For you to show us hydrogen, you need to put a 2. So they should have used the 2 times this guy. So this is something you take note of. There was an error here. Then look at the other one here. They're saying calculate the number of moles of a gas at 1.5 atm in this volume at this temperature. So meaning if you're given such a question, this is simple for you that are doing Chem 1000 because now that you've done gases, you know, just compute here the value of R that you use. There are so many values of R. The one that you use is the one that has matching units with the pressure that you are given. So pressure is in atm. We're going to look for the universal gas constant that has atm. Remember they used the 0.08206. That's how they got there. That's how they got the moles. So you can just try to compute this. Try to answer this question that says home practice. So this meaning you have the number of moles that we're looking for. We're going to use concentration times volume. Your concentration is 0.033 moles per liter and the volume is simply 0.025 liters. So the units, this you know they will cancel when you multiply. So let me just write this here. So mole per liter multiplying 0.025 liters. So the liters cancel. You multiply this, you get your moles. So that's what you have. So now the whole idea is that whenever a reaction is taking place, there is always some reactant that is going to be limiting the whole process, or rather there is some reactant that finishes fast, that is in lesser amounts, and that's what you call your limiting reagent. And before we do that, I'd just like to point out something here. There's this guy that we call mass percent. So mass percent is, if I was to give you to say there is 10 grams of carbon dioxide, then I want you to find the mass of carbon in this carbon dioxide that was given. So you first of all get the molar mass of this. The molar mass of this, I'll just get it to be 44 grams per mole, because if you do this is 2 by 16, that's a 32. Then you have what, 1 by 12, this is simply 12, we are getting a 44, right? The contribution of carbon is 12, right? So you simply say the percentage of carbon in carbon dioxide is simply, you simply do your 12 over 44, then multiply that by 100%. What do you get? So if we were to punch this, we're just saying this guy divided by 44. So I'm getting a 27.3%. So this is the percentage of carbon in what? In carbon dioxide. So now if I want to get the mass of carbon, I'll just say 27.3% over 100%. Then I multiply this with the mass, which is 10 grams. So this times 10, then divided by 100 is simply, this is a 2.73 grams. So this is simply going to be the grams or the contribution of carbon from the 10 grams carbon is only occupying or having the mass of 2.73. The same would be done for oxygen as well. You simply use the 32 over 44, you get its percentage, then you'll be able to get the what? You'll be able to get the mass. Now, there are times when they give you percentages and they're asking for the empirical formula. So these are some terminologies I need you to know before we dive into the calculations. So when it comes to empirical formula, this is just a formula with the smallest atom ratio. So for example, I'll give you something like C2 this. This here is the actual formula of this guy, which is methane. And the empirical formula for this is just CH2. So the simplest ratio, if there's a number that can divide this subscript, we use it and then we reduce it. So this here is what we call the empirical formula, the empirical formula, the EF. That's what we need. The smallest atom ratio type of formula. That's what we need. And that's what you get when you use your percentages. So remember, we got from carbon dioxide, we said the contribution of carbon was 27.3, right? So meaning the contribution of oxygen is simply 100 minus 27.3, which is what? Which was 72.7%. So now if I'm looking to find the empirical formula of carbon dioxide, I'll just divide this by 12, the mass number of carbon. Then for oxygen, I'll just use the 16. I'm using the whole numbers. Then I'll divide this guy by 16. This is a 4.54375. Then this side, if I divide 27 by 3 divided by 12, I'm simply getting a 2.275. At this stage, you divide by the smallest number. So the smallest number is this. Even this side, you divide by the same. So now the first part will be a 1, then the other part will be 4.54375. So we are simply getting a ratio of 1 to 1.99, which is the same as 1 to 2. It simply means carbon there is 1 and oxygen there are 2. So this is the empirical formula of carbon dioxide. So this is easily seen if I give you three things. So if you are given 3 compounds, of which they all have their respective masses, so you see the total mass of the sample was this mass here, but each one was having a certain contribution. So we can just get the percentages. So we have the percentage of each particular atom, and these percentages are going to be used the same way we use the one for carbon and hydrogen and oxygen. So we can take them as grams, or rather take them as percentages. It's okay for someone to write percentages here. It's okay even if someone is wrong, because these are still the percentages. Yeah, the mass percentages. We divide by the respective mass numbers, we get this. Then here we divide by the smallest, which is 1.789. So you notice we're getting a 2.8, which can just be a 3. This is a 6. This is a 1. There is no number that can reduce this expression. There's a 3, 6, and a 1. So no number can reduce them all. So this here becomes our empirical formula. So that's basically what we do if we want to get the empirical formula. And the last thing I should mention is that in as much as we want to discuss the limiting reagent and the titrations or the necessary equations that you need. But before we do that, we always have an expectation of what we need to get, right? So they will give you this percentage yield is what you've actually gotten. So actual yield from the experiment, this is what you get. So percentage yield is the same as the actual yield divided by the theoretical yield, then multiply this by 100%. Theoretical yield is what you are given in the question, the mass given in the question. Then actual yield is the mass that you calculate. The one that you calculate, that's the one that's actually there. So the bigger the number of the percentage yield, the more pure your substance is. Yeah, so this, you must know this. When we say calculate the percentage yield at some point, this is the formula that we'll be using. Okay, so here we are back again here now. We want to discuss limiting reagent and how we calculate it. So we need to always know what is going to be limiting the experiment. It's like you want to cook and then power cuts. What is limiting you is the power that has cut. Everything else is in place. Yeah, so the same applies to these reactions we'll be dealing with. And once you know the guy that's limiting, it's always easy for you to find out how much will be produced. So look at this example here. Hydrogen cyanide is produced industrially from the reaction of gaseous ammonia, oxygen, and methane. So they've given us the mass of each thing here, they're the same. So they're all having the same mass, and this is the same as 5 grams. This is like 5 grams here. Then you have 5 grams there, and you have 5 grams there. So they gave us the 5.00 times 10 to the power 3 kg. So these guys here were in kilograms. I just converted this to grams, so I divided by 1,000. And if you notice, the equation is balanced. So this is what we are having. The masses are all the same. They said each has this mass. So this was very straightforward. So now I will divide this by the mixture of ammonia. So the mixture of ammonia was simply 17.04 if you get the mixture, the molar mass. So these are the masses. I'm trying to get the moles, right? So I'm dividing this by 17.04 grams per mole. Then for oxygen, I'm dividing this by, I'll use your 32. So let me use the one that was given here. So we are having 32, so I'm going to use 16 by 2, so this is the 32 grams per mole. Then for methane, the mixture for methane is simply 16.05, so I'll go with the 16.05 grams per mole. Now if you divide this, you're simply getting the moles. So you notice that the first answer you are getting, when you divide this, that's 5 divided by 17.04. So this gives you something like a 0.293 moles. Then for the second one, you're simply getting 5 divided by 32, which is a 0.156 moles. Then for the other one here, you're getting a 5 divided by 16.05. This is a 0.312. So you notice all these are moles for each of the reactants. Now the ratios that they were in, and please be careful that on getting the mixture, we're not going to use the numbers in front. These numbers here are purposely for the balancing of the equation. They are not used whenever we are calculating the molar masses. Yeah, so these are the number of moles that you are getting. Now to neutralize this, to compare them to a 1-to-1 ratio, we're going to divide by the numbers in front. So here there is 2, meaning I'll divide this guy by 2. Here there's a 3, I'll divide this by 3. Here there's a 2, so I'll divide this by 2. The reason why we're doing this is because the number of moles you've gotten here is for 2 molecules of ammonia. We need to compare them to a 1-to-1 ratio. And how best can we turn 2-to-3 to 2 ratio? How can we make it to be a 1-to-1 ratio? The best way we can only do that is by dividing by the numbers themselves. So this will now be a 1-to-1 ratio. And if you do that, you notice that the first thing, 0.293 divided by 2, this is 0.1465. Then the next one, 0.293 156 divided by 3. This is 0.052. Then the last one, 0.312 divided by 2. That's a 0.156. So the smallest number here is the one for oxygen. So oxygen is simply the limiting reagent. Yeah, so we just have to identify the correct limiting reagent. So here, if you notice that the one for oxygen is less than all the others, so we're saying oxygen is a limiting reagent. And once you identify the limiting reagent, everything else becomes easy, because the next question that they'll ask is for us to, let's say, find the mass of this guy that was produced. What mass of this was produced? So once you know the limiting reagent, all the other calculations will entirely depend on it. So we can now remove the other guys, and we remember what we got here. When you divide the 5 by the one for oxygen, I'll write this in red. So the mass, that the number of moles you got for oxygen was 0.156. When you divided by the moles, when you divided by the mass and the mixture, this is what you got, right? So if they're asking for the mass of hydrogen cyanide, these guys are in a ratio of a 1. So oxygen is 3, so 3 to 2. So oxygen has 0.156 moles. Then how many moles will this guy produce? So meaning the moles of our hydrogen cyanide will entirely depend on this. So we multiply the 0.156 by 2, then now divide it by 3. So the number of moles will be this part. This is the moles of the hydrogen cyanide. Using this equation, you can now get the what? You can get the mass of the cyanide that was produced, because you have the moles 0.104, then times the mixture of our cyanide. If you just go back, the mixture of our cyanide is 18.02, so multiply this by the moles. So we are getting what? We're getting this is for the cyanide. Yes, the cyanide is 20. This is a 27. So here there should have been on top here, there should have been this part here, oxygen. No, not this 5. This is not supposed to be there. It's supposed to be a negative because of this. You notice the oxygen. So the oxygen, when you got the moles of oxygen initially, what you got was okay, so this was supposed to be division, because we need to convert this to grams. So here they made a mistake here. So you need to follow these calculations here. So this is the moles that we have. This is what we are putting there. And if you do the conversion, these are the moles of the hydrogen cyanide. Now hydrogen cyanide is 27 something. So 27, this guy by 27. Here I'm just getting a 2.808 grams. So this will be the mass of the hydrogen cyanide. But then you can convert this to kilograms. You multiply it by what? By 10 to the power 3. So now it's going to be in kilograms, is it? Yeah, so this has, no, we have 1 kg is equal to 1000 grams. So how many kg will give us 2 point? It's supposed to be divided. This is supposed to be a negative like that. Yeah, if you want to put it in kilograms. But this is the general idea behind identifying the limiting reagent. So here, please do ignore these errors. As long as you got to understand how we identified oxygen to be the limiting reagent, then that should be okay, because all the calculations that we'll be doing will be based on these 3 first equations. Yeah, so there's already a video on oxidation and reduction. So I'm going to give you one last illustration on stoichiometry, which has to do with titration, because everything that you've learned just has to be applied whenever we are dealing with experiments that are complex, and titrations are the best ones to start with. And we have 2 types of titrations. So titrations, there are 2. There is forward titration, and then there's backward titration. There's back titration. Yeah, so by looking at a question, you can tell whether a question is a back titration or forward titration, depending on what they're asking for. So if the missing quantity is on the first equation, in an event where you have two equations, like number 2, if you look at number 2, question number 2, what are they asking for? They're saying how many milliliters of sodium hydroxide is used. They're asking about this. That's the only time you see sodium hydroxide. There's no sodium hydroxide here. The only time you see sodium hydroxide is there. So meaning this is going to be a forward titration because we're coming down like this, right? What we are in need of is in equation 2, so meaning we just do the forward way. But if what we're interested in is in the first equation, like here, look at this. What is the identity of the element or the metal M, which is in the first equation? So meaning we're going back like this. Our calculations will be backwards. That this here is a typical illustration of back titration. So now to make life a bit easy and applicable, I'll show the solution to the question 1 and question 2 that were given in the Chem 1000 assignment 1, the one that you submitted. It was called assignment 2, the first submission you made. So here is the first question, and I'll be honest, there is no format that we may say this is how we go about when it comes to titrations. All questions are different and unique, so the way you tackle them depends on what they're asking for. So look at this example. They are saying a 1.1664 gram sample of M hydroxide was mixed with 25 milliliters of the 3.00 molarity hydrogen chloride, and enough water was added to make 100 milliliters of solution A. So I need you to write the data. So this is how you do it step by step. Look at what I wrote here. So I wrote the mass of the first thing. This is what you have there. The mister, we don't know. Then we have the volume of the hydrogen chloride, which is there. The concentration was also given. So this is the information about the first equation. I put the volume here in between the two guys because the water was added after these two guys react. So they said was mixed with the HCl, and so the addition of water came after. They are saying, and enough water was then added to make a 100 milliliter solution A, right? So you need to always be careful and be cautious of when the water was added. When did they dilute your expression to increase the volume? So these guys first of all reacted. Then after they got done with the reaction, what remained, they added the 100 milliliters to make up solution A. Then now from the solution that they made, they got an aliquot, which is just a portion or a sample. So from the 100 milliliters, they got 10 milliliters, and then they reacted it with the base, which is sodium hydroxide, with the volume and the concentration given like this. So now this is a perfect example of back titration because what we are looking for is in the first equation, right? We're looking for M. M is in the first equation, so meaning we're going backwards. And if we're going backwards, you need to notice that between the two equations that you are given, the thing that is appearing in both equations is hydrogen chloride, the HCl, the acid. So meaning from the first equation, this guy was limiting. This is the one that is in excess. This guy, so this guy is limiting the reaction because after HCl dealt with the metal hydroxide, what remained was brought forward to be dealt in a neutralization reaction with the sodium hydroxide to produce salt and water. So now, if you have noticed that the HCl was in excess, we're going to start our calculations backwards, and this is what we're going to do. So first and foremost, we have the volume and the concentration of the base down here. Remember, our calculations are going to be made upwards, so we can get the number of moles. So the number of moles, so you convert this guy to liters. This guy in liters will be 0.02 liters. This is what you're seeing there. You know to say 1 liter is equal to 1000 milliliters, right? Yeah, so please take note of that. So that's what we have done. So this is the number of moles that I got. This is the number of moles of the base. This is what you'll get. Now, if this is the number of moles for for the sodium hydroxide, the equation is balanced and these guys are in a ratio of 1 to 1. So if they're in a ratio of 1 to 1, you see this is 1 to 1, we can assume that the same number of moles of the sodium hydroxide will be the same number of moles of the HCl. So that's the reason why we are calling it here to be the same. And we call that to be excess because the one that came to the second equation was excess. From the first equation. So we call this excess. Then from the initial data that you are given initially, we have the volume and the concentration. So we can convert this. This is 0.025. This is liters. Multiplying the concentration and the volume will give you the initial HCl before the reaction started. This is what you have, right? So I've just gotten the initial number of moles. This is what we've gotten here. And the excess number of moles of HCl that we've gotten were found in the 10 milliliters aliquot. Remember, we made 100 solution, 100 milliliters, and we tatapamoche 10 that we brought to the second equation. So we have to make what you call your volume ratio. So your volume ratio is simply saying that in 10 mils there were these moles. So these were the moles present. How many moles will be in the 100 mils? So we don't have to convert this to liters because they will eventually cancel out. So we're saying these were the actual moles in the excess, which were added in the 100 mils. So now that we know the actual excess, we can subtract them from the initial to know how much was used to react with the metal hydroxide, to react HCl to the metal hydroxide that was given. So this is why we're doing this. So this is the number of moles that was needed to deal with the metal hydroxide, and we will then relate the mole ratio between the two things. We're not just going to say the metal hydroxide is in a ratio of 1 to 2 with the HCl, so we can get the number of moles of the metal hydroxide. Once we get the number of moles for the metal hydroxide, we can bring back the equation for number of moles is equal to M, mass over molar mass. Now, you know to say the mister has been gotten here. So the mass was given from the question. The number of moles you do have, you've gotten them from here. So now you've gotten the molar mass to be this. This is what you've gotten. And you know how we get molar mass, right? Molar mass should have been 2 by the mass number of hydrogen, then 2 the mass number of oxygen, then 1 times the mass number of X. We don't know what the M is. That's what we're looking for. So now I've just put X. So when you combine X plus 34, where the 34 coming from? The 2.016, and this also is 32 point something. So when you add these guys here, when you add them, they'll give you 34, then plus X should give us 58. Now we're solving for X, so X will be 24 point that. We go on the periodic table, we look for something that has the 24, so that's how we found our M to be simply the magnesium. So this is how we got the magnesium. This is what you have. So this is a typical illustration of the back titration type of question. So like they said, you notice here they said in a logical reasoning, because there is no rigid way that will say, no, this is how you always solve back titration. No, it varies. You just have to follow through the steps and use the formulas that you learned under more concept. Yeah, so this is what you are supposed to do. So the next one, the next example here, they were just saying a 0.69 grams 910 gram sample of potassium carbonate is dissolved in enough water to make a 200 milliliters solution. Then from the 200 they just got a 20. So the aliquot here is gotten after the mixture is made only in potassium carbonate before they reacted with the acid, and then they put in an lamellar flask to react with the HCl. After this equation is done, the resulting solution is then titrated with 0.15 concentration of sodium hydroxide. They were interested to get the volume of sodium hydroxide. That's what we want. So now the first thing that we do is right here. I'll show you how we go about this. So write the equations with the data, of course. So you notice how I nicely wrote down the data from the question under every particular molecule. So we wrote for potassium carbonate, I wrote all the information that was given. So using these two, I'll get the what? I'll get the moles. But those moles are going to be found in the 200. So you need to get the actual moles in the aliquot. So hope you're seeing what we're doing here. We get step 1, we get the number of moles of the what? Of the potassium hydroxide. Now these moles are in the 200 because they now added water and made a volume of 200 milliliters. Now we just want the number of moles in the 20 milliliters because we only got 20 mils of the potassium carbonate to react with the HCl. So that's the reason why we're doing this, so that we now know the number of moles that reacted. If you know the number of moles of potassium carbonate that reacted, you can do your mole ratio now with HCl to know the number of moles of HCl that was used. So this is the one that was used to react with the potassium carbonate. If you know the one that was used, and then in the question they gave us to say, in the lamellar flask you had this is the initial information about HCl. So you can use this and that to get the initial number of moles. This is what you are seeing here. Please don't forget to convert your volume to liters. So that's what we get here. This is the initial number of moles. Then now we find the difference between the initial and the used to find the number of moles that was in the excess. So the excess is the one that we brought to the second equation, the one that reacted with the sodium hydroxide. So this is the excess, the one that remained. And if we do the mole ratio, these are in a ratio of 1:1. So the same number of moles for HCl will be the same number of moles for the hydroxide. This is simply what you get. Now, they already gave us concentration in the question. So we have the concentration and the moles. We can do that to get the what? To get the volume. Once you get your volume, which is in liters, you convert it to milliliters because the question was saying we leave it in what? We leave it in liters. So we give them the answer now in milliliters because they needed the answer to be in milliliters. And then the last question, they're just saying calculate the percent by mass of the potassium carbonate in the sample. So now that we know the potassium carbonate that was used, or the one that was used, so according to our number of moles, so here on the last part we needed to use the number of moles that we used. So this is the used number of moles for the potassium carbonate. So this is the number of moles for the potassium carbonate that reacted. You have to use this number of moles, the 0.0005 moles. You react it, or rather get the mist as well. The mist of potassium carbonate was given to be what? So we have this is 138. You say 138.20. That, so if we multiply 138.20, then multiply it by the number of moles. So this should give us something like a 0. So here the mass that I'm getting, if I use this, I'm using this formula. The mist, I'm multiplying these two. So the mass I'm getting is 0.0691 grams. So if this is the mass that you are getting, we can just say percentage by mass. This will be 0.69019. This is grams divided by the actual mass. The actual mass on the question, was 0.6910. 0.6910 grams. Multiply this by 100%. So this should give you something with what was used and what was initially given. So this is divided by 0.6910. Yeah, then you multiply this by 100. So this should give us something like a 10% is the only thing that we used of the sample. Yeah, so there are so many ways, I must say, on how you can go about the last part where you get the percentage, because someone will argue to say, why are we using this number of moles, which was in the aliquot, instead of the actual number of moles? The reason why I've used this number of moles is because it's the one that was used, or the one that participated in the reaction. Yeah, so the other one did not participate. We didn't use the whole lot of the 200 mils. We only used 20 mils. So that's the reason why I'm using that. Yeah, so this brings us to the end of stoichiometry. If you're interested to To register for lessons, to access full videos, you can feel free to WhatsApp me on this number. And if you have any questions, you can still WhatsApp on this number for clarifications. And for redox titration balancing equations in acidic and basic media, there's a separate video on the channel. You can just scroll through under videos, you'll be able to see it. Thank you so much for watching.